Okay, good day to everyone. I hope everyone had a good weekend and stayed safe. I'm going to talk briefly about some of the changes to the proof theory that are related to the um, splitting of responsibilities in terms of width and depth, or breadth and depth, for the modal operators, and hopefully those notions will become clear in a moment. Let me screen share. Hopefully everyone can see. Okay, so we've revised the types a little bit, um, and introduced. So we have a slightly different notation for false. So we're using the empty set for false and top for the entire generated language. Um, One is lying around because we have a Levere theory, so we added that. So these are the basic constants that come just from the underlying notions. And then because we have sets, we necessarily get complement and union. Um, we have if the operator is not commutative, we insist on having uh, at least a left or a right identity, or both. If the operator is commutative, then these coincide. So you have to have at least one of these two. Um, and so, like, lambda does not have a right identity, but it does have a left identity, as an example. And uh, the row calculus is commutative, so these two coincide, and they're both zero. And then whatever other constants you may have imported. So all of this is coming from, um, so this stuff is coming from the collection structure. And then these are constants from the term language. And then this is the basic constructor from the term language. So we're assuming that the term language has at least one binary constructor, and that's the source of the red X, right? So when you put terms of a certain shape in the binary constructor, then it reduces. So these are types for interaction. And then there we deny the interaction without the resource. So you have to have a resource. So we can also lift that to the type level. And then because of that, we have a notion of you can put things in K but deny the resource. So that's this way. And this is designed to unpack those. You can also put them in, so if you think about this as wiring circuits in parallel, and this is wiring circuits in serial, and this is unpacking the serial constructors. So we'll make sure all of that is clear in a bit. And then we have a notion of an arrow. So you have both a right arrow and a left arrow. And we're careful to only, you can build up nested arrows, but the arrow is not is stratified. These are lambda terms representing context, and these are basic terms. So hopefully that makes sense. And then the one really new operator is given n r's that would allow you to go a single step. This gives you a single step in the arrow, in the rewrite rule. So this says, if you have n r's, then after a single step that uses up all the r's, then you become something that satisfies T. So that this is distinct from the arrow, and we can talk about the arrow model theoretically right here. So if we want to look at just the right arrow, and in general, this is going to be parametric over k. You might have multiple k's. So and if there's only one k, or if it's clear from context, then we can drop the k, which is what we do down here. So if I have a type tau and I have a type tau prime, then the model theory, and again, it may look like we're using sets, but really this is intended as a comprehension notation. So if we think about this as some comprehension language that allows us to collect things using an appropriate monad, that's the way to think about this, the model theoretic concerns. So it's going to be all the u's such that there exists a t such that u decomposes into a context. Right, so we're collecting context. U is a context, and t is in the left-hand side of the k. So your whole is here, and t is this quantified term here that's in the left-hand side of the k. And for all u prime in tau, so this is your tau here. So for all the u prime in tau, if we apply u to u prime, so this is a lambda term, so we can apply it, then that goes in a single, if there's a rewrite that takes it to some v, then that v has got to be in tau prime. And the other facing arrow is, of course, just putting the term on the other side. Is that clear? Any questions about that?
Yeah, it's clear. It's clear to me.
Okay.
I
good.
just want to ask you about the types. What does it mean, underscore?
This is to distinguish them from the constants. So here,
Okay.
yeah, so we can tell at a glance that I've got a type versus a constant.
Okay.
Or a term constructor. Okay. Then we have some abbreviations. So in particular, one that's useful is tau perp, which is just tau right arrow RK, and so on and so forth. Okay, so now we have some axioms. So the constants are typed according to their lifted logical operator, right? So C is always going to be C without a C underscore, without any, hypothesis necessary to establish that. The same with the identities. And then axiom is just that under the assumption that X is of type tau, then we can conclude that X is of type tau. Notice that as soon as we do this, we've moved into a kind of intuitionistic land. So you've got potentially multiple inputs and a single output on the right-hand side of the turnstile. So we're still working out the story for the classical version, right? So you can think of this as an intuitionistic version of a linear theory. Okay, so then just as you would expect, if you're going to form a row tensor, then that's just forming a K. So you'll notice that when I do form Ks, I have a choice about whether to declare it a tensor or a serial, and what that that means that the type assignment is intentional. The program is giving us information, as opposed to there being a principal type, right? There's a choice here in the type system. So these are your standard term formations, and then here's the place where things get really interesting. This is just a consequence of this, so you don't have to worry too much about that one. You can work it out for yourself. But this one says, suppose I have a par that I've gotten from gamma, and suppose I have a tensor that I've gotten from delta, right? So here's a k, which is a tensor. Here's a par thing, which I've typed as a par. And then I can cut the two together. So I need all the gamma and all the delta over on the left-hand side. And then I'm going to form the I'm going to cut T1 with T1 perp, and let me see if I've got this right. Yeah. So we're wiring up the T1 with the T3, and right. So T1 is going to go with T3, and T2 is going to go with T4. Right. T1, T3, T2, T4. Right. So I'm applying a K to those arguments, and then I'm supplying them with enough gas to run, and I'm wrapping whatever the results are in K. And I'm under certain assumptions about contextual evolution. Then this is typed RK. So you can see that you can see that this thing is of type T1 perp, and this thing is of type T2 perp. All right, so I should probably relabel these. But anyway, tau one. Sorry, this is of type tau one perp, and this is the type tau two perp. Right. So T1 is effectively going to be tau one perp, and T2 is going to be tau two perp. So and then T3 is going to be tau one, and T4 is going to be tau two. So when I cut a tau one with a tau one perp, right, that and a tau two with a tau two perp, right, this should result in an identity, and this should result in an identity. So I'll have identity here, so that should be the identity. All right, and we don't have to, assuming that these can go under the K, which is a strong assumption, then these two will go in a single step, right? There's nothing preventing them, no sequentialization necessary here. So they'll go in a single step. And since they'll be identities, and they're both going to be identities, then K of the two identities is just the identity. So this is going to be true in terms at equality, right? So there should be an underscore here. That's a mistake. There should be an underscore here. That's a typo.
Can I ask you why is this identity?
So tau one perp with tau one, so they annihilate each other and produce the identity. Tau two perp and tau two, they annihilate each other and produce the identity. So I have an identity here, and I have an identity here. K of two identities is just the identity.
And why? I mean, you want this to be on purpose identity, right? To annihilate each other.
Yeah, that's right. This is the property that we're giving here is termination.
Oh, I see. Okay.
You get more properties by putting different things on the right-hand side of the arrow. So if you could define whatever kind of property you wanted up here, right? So this perp is really just a shorthand for the identity. You could get a different property. Yeah, you get a different property if you use this. So you get lots of these different kinds of rules. Right.
I see, and we will end up with, of course, a different type.
Yeah, that's right.
I see. So this is like a special case for termination.
Yeah, exactly.
Okay.
So then this part is, we're still sort of thinking about this, but you have to have it as a side condition. So if you're going to do lambda formation, so gamma together with the assumption that X is of type tau, assuming that that gives you that RK of K TX is going to be top tau, so we have no constraints on T. Then we'll get that when you do the currying, right? So you move the X over using abstraction, then this is going to be of type tau prime, right? So we're shifting what we, yeah, we're basically doing our currying. But that's under the assumption. So this wouldn't hold unless you assume that for all u and tau, anytime there's a rewrite from K T U to V, V is in type tau prime. So that's the right arrow, and the same is true. You know, you get a corresponding thing for the left arrow. Now, you get a corresponding cut, right? So you have there's a lambda version of this. So if I have that gamma gives me a context that's of type tau to tau prime, and delta gives me that u is of type tau, so there's my argument. Then this RK is of type tau prime. So it's really in a single step, this is going to be of type tau prime. And then over here, you'll get the same with the arrow going in the other way. So it just means you put the argument on the other side of the K. And additionally, you have the serial composition. So now this term here is putting T2 and T1 together serially. And here we're assuming that this is T2 to, tau2 to tau1 perp, and this is tau2. And over here we have tau3 to tau1 and tau3. So when we cut them serially, so we're going to cut T1 with T2. Okay, so here's T1 and T2. So we're going to cut these two together first. So this thing is of type tau2. This thing is expecting tau2. So this will result in a tau1 perp, right? That term here will result in a tau1 perp. Over here, we have a tau3 and a tau4, or sorry, T3 and T4. T3 is of type tau3 to tau1, and this one is of type tau3. So this one is expecting a tau3, and this one is a tau3. So when we cut these two together, we'll get a tau1. So now we have a tau1 perp and a tau1, and they're cut together. And that will give you an identity, right? And so then you'll get the identity, but after one step, right? So these don't go in these don't, like here, you're in a single step. After these reduce, you're already at RK. You're not at RK. You have to run the outer K. So you need to say after one step. And that's where this thing comes in.
And when you say one step, because we are talking about rewrite to rewrite, are you thinking about one step on the rewrite level or on the underlying language on which
No,
we're describing?
the rewrite is the language, right? I mean, that's all we've got. We've got terms that rewrite. So it's one rewriting step.
I see.
So, yeah. So here we don't count these inner ones in some sense, but this outer one has to be done because this is really all these terms, all these types are after a single rewrite. That's really the arrow says after a single rewrite. And so here we have one more rewrite to do, so we have to account for it, and that's where this one comes in.
I see.
Yeah. So go ahead.
I was just thinking now it's more clear to me the difference between parallel and serial. Yeah. And it seems that in serial we have the lollipop included in the type, and in parallel this is somehow implicit because they are combined. It's between left and right in a sense.
Yeah. There is a lollipop, right? Notice we have a perp here. So a perp is really tau lollipop RK. So this is really tau lollipop RK. And so when you cut a tau one a lollipop RK with a tau one, well, the tau one goes in for the argument, you get an RK out. Likewise, this is tau two lollipop RK. So you supply a tau two to a tau two lollipop RK and you get an RK out. So you're going to get an RK here and an RK here. And now Ks of RKs is just RKs.
Oh, I see it now. Thanks.
Sure.
Yeah.
Yep, that's it. So that's how things have shaped up. As I've said, we get the lambda. So like the lambda that we have here, we get that lambda because we move to. So we go from the resource. So we start with a Levere theory. So here's your Levere theory, right? And then you resource it. So you add a single map, and then you can contextualize it. And this contextualization is just moving from an ordinary Levere theory to a higher order algebraic theory. So allowing us to have, first class context. And that's what allows us to express the lollipop. And you can really think of the lollipop as a generalization of beta. So, so here's beta, right? But what we're really saying is that we're not just doing beta. We're saying that anytime you have a rewrite like this, you go in a single step, and it's only for it's only for the ones that are in tau. So it's kind of like splitting beta into two pieces. So that's one way to think about it. And so it's a very natural. It's like we're how do I say this? We've kind of abstracted the data. Here's the way. So Milner points out that you can think of the reduction in pi as first, getting the data and the lambda term at the same location. And then once you got them at the same location, then you do the data exchange. So there's synchronization and then data exchange. So it's the same thing is going on here. We're just generalizing his idea. This K is providing you with some, There's some kind of synchronization that happens, and then there's a data exchange. That's really what's going on. And yeah. Go ahead.
When you say synchronization, I cannot connect this to something.
Oh, so synchronization is the output and the input lined up at X. They synchronize. So in Lambda, the way output and input synchronizes, they have to be next to each other textually.
Oh, okay.
Right. So that's the only synchronization is you got put on the circuit board next to each other. Right, because the term is physically wired up, right? And then pi or rho says, no, you don't have to be physically next to each other. You just have to refer to the same location. So they, the inputs and the outputs, they swim around, and then if they land at the same site, right, then there's a data exchange. And you could imagine much more complicated synchronization, and I give a really good profound example of that with the annihilation rule, right? So we say that landing at the same site is reducing the terms that represent those sites, right? So it shows you that synchronization itself can be completely programmable. So it's synchronize and then data exchange. That's the idea. And this is just typing that, right? This is just saying abstractly there's some kind of synchronization, and then there's a data exchange. And when you do both of those things, then you have to go from a tau to a tau prime. And that's what the lollipop is.
Yeah, this makes sense. I mean, in Lambda, this is like so obvious that it's like directly written, so it's not something that you need to think about, right? Yeah.
Right. That's the problem. Is the synchronization in Lambda is invisible
and not dividable, right? You cannot escape it. It's always there.
You can see it. You can see it poking its head out in De Bruijn indices. The De Bruijn indices give you the synchronization scaffolding, right? The De Bruijn indices are telling you where the wires are.
Oh, I see.
Yeah. So anyway, so that's kind of the shape of things as we are thinking about them now. I'm pretty excited because, as you can see, we have both the Hennessy-Milner style. So you could easily write this as a after tau, then k of after k of tau x, go to tau prime. So you can write this literally as a Hennessy-Milner modal logic expression. So we're connecting the linear to the modal, but notice that this is only width-wise, right? So the width is the for all. So this is a necessity operator as opposed to a possibility. If we change this from a for all to there exists, then we would get possibility instead of necessity. So that's the width part. And then how deep you go is the circle part, right? So how many arrows you go. So we're assuming you get the first one from the R, sort of, but any further steps you have to mark, and that's depth. So this is the marking in terms of the depth. And notice that you need the N and not just a singleton, because, for example, in this one, these two go at the same time. So it's only with two R's, right, that you will step forward. If you only had one of these R's, you won't step forward. So you have to have an N. So we'll give a little preview for next week. Next week, we will be talking about the what's in the industry or the research community called MPC in the head. So this is a multi-party computation. So what Rho is really good at in the head, meaning that it's imagined by a prover. So in particular, a prover is internally running a protocol to amongst several different parties, several different processes, and then it turns out that you can turn that into you can give witnesses from MPC in the head to a verifier, and the verifier can get a zero knowledge proof, or the whole arrangement can give you a zero knowledge proof of what you've done. And this is distinct from circuits. And the interesting thing is that these people are looking at this in the abstract. They haven't realized that there are really good calculi for writing down those kind of protocols, like the Rho calculus or the applied pi calculus. And as a result, you can get all of the artifacts that a verifier might use to verify a given computation from the structure of the calculi. So that's what we'll be talking about. And the reason that becomes interesting is because now you're not verifying circuits. Part of what makes circuits so problematic is that they have serial execution. And with a Rho term, you don't have serial execution, and as a result, you can do parallel analysis of the evolution, right? So especially if you have evolution that's proceeding in parallel, you can do parallel analysis of the views, which would then speed up your the time to verification. So we're honing in on starting to make zero knowledge practical inside Rho. So we started with, can we represent these protocols? Can we reason about the complexity? And we showed that all of that was absolutely possible within the Rho calculus, which we knew it had to be, right? Because Rho is Turing complete. So that had to be the case, but we just wanted to make sure that we sort of understood how that story went. And now we're moving from there to efficient implementations of zero knowledge inside Rho. And that connects us to the MPC in the head line of research. And so we'll be talking about that next week. All right, I'm gonna leave it here. Thank you all for coming, and looking forward to next week's talk. Please stay safe.
Thanks, Greg.
Cheers.
Thanks.